Hello, everyone, and welcome to our fall season. Our featured guest is Dr. Michael Blanton from NYU's Cosmology and Particle Physics Department. Mike received an undergraduate degree in engineering and physics from Cornell and his master's and PhD in astrophysics from Princeton University. Mike's additional interests include hiking, landscape and astrophotography, as well as giving outreach lectures to such groups as ourselves. In the late 1990s, there had been a bold undertaking by New Mexico's Apache Point Observatory. In conjunction with several universities, the goal is to produce a three-dimensional map of the universe. To date, there has been the detection of over 3 million galaxies with more to come. Mike has dedicated his research towards optimizing the capability of the Sloan Sky Survey. Apparently, his efforts did not go unrewarded. In April of 2012, an asteroid, which had been discovered by the Sky Survey in 2001, had the name of 14090 Blanton conferred upon it. So please give a very warm welcome to Mike.
Thanks. The early imaging survey had detected sort of serendipitously a whole bunch of, like hundreds of thousands or thousands at least.
No sound.
Yeah, that works. Can you hear me online? Okay. So thanks for having me. I am not an amateur astronomer. The only skill I have in amateur astronomy is I teach a class at NYU where we go to a rooftop and teach the undergraduates how to use a small telescope from a rooftop in Manhattan, where the sky is rather bright. So it's enough to fill in a semester for undergraduates who have never used a telescope before. And that's the limit. The end of that course every year is the limit of my expertise in using small telescopes. I started as a theorist before I got involved in this survey. And so anyway, I'm going to talk about the Sloan Digital Sky Survey. This is a survey that these days uses 3 facilities, one in the Northern Hemisphere, the Sloan Foundation Telescope, and 2 at Las Campanas in the Southern Hemisphere, the DuPont Telescope, and a set of small telescopes that I will describe. And this has evolved over a large, since really the beginning of the 90s, before I really started in astronomy. And I'll describe a little bit about the origins and the ambitions, but also describe how it changed over time, because the project, has proceeded in a bunch of phases, like 5-year phases, and at the end of every phase, we burn it all down and decide what to do next. We metaphorically burn it down. and decide what we're going to do next. And currently that we are in that process right now. And so the project has changed a lot over time. You know, we started by doing a map of the universe and delivering that, you know, to the public and to astronomers, sort of changing the way people did astronomy. We did all of that from New Mexico. Then we decided to go to Las Campanas because it turns out that the stars are in the southern hemisphere primarily. We did all that with these spectroscopic plug plates I'll show, but nowadays we have replaced those with robots, as I'll talk about. And most lately, we have been doing this project with these to us, very tiny telescopes that are nevertheless very powerful. So the beginnings were in the late 80s. There were a couple of technological sort of developments that were clear to some number of people were really going to change astronomy. One of them was the development of CCDs, digital detectors, and although they were very, very expensive to make very, very small ones, it was clear that over time, these things would become more efficient ways to observe the sky than what had been done before, which, you know, was these glass photographic plates with emulsions and stuff, which are very inefficient. And so you could conceive of doing a large imaging survey with the CCDs. At the same time, fiber optics was, you know, becoming better understood and better developed. You could go to a company and get a large, you know, fiber optic cable, and that was a way to deliver light. So the imager, of course, just images in the focal plane. If you want the spectrum of an object, you have to deliver the light to a spectrograph, either through a complicated set of optics or through these fibers, which, if they're efficient enough, and these days they're rather efficient, can map the focal plane to your spectrograph in an efficient way by arranging the fibers properly. So these two developments, primarily Jim Gunn, but also Rich Crone and Jill Knapp, you know, basically realized you could do a large survey of a big chunk of the sky and get redshifts of galaxies, a million, and they estimated 1 million galaxies, which is basically what they did in the first phase of the project in the end. And then you could produce a digital map of the universe that way. So this was very exciting. They came up with this in the late 1980s, put together a collaboration. They realized that they needed a lot of money, which was like $12 million. So they went to the Sloan Foundation to help fund it. And at the beginning of the 90s, they thought they would be taking data by 1994. There's a whole book about the Sturm and Drang surrounding the beginnings of the project and the difficulties that they faced of various sorts by Ann Finkbeiner. It's a great book that I recommend. But I'll point out, like, yeah, it was late. People were mad at each other. It was like, you know, it was nerve-wracking. But, you know, by late, it was a project they started basically in 1990. They thought they were going to be done building the thing in 1994, which was just a ridiculous idea that they would be able to build a telescope and all this instrumentation in that amount of time. And they did it instead in 1998, which actually is a pretty reasonable timescale for what they wanted to do. And from this perspective, looks like, 4 years. Of course, the graduate students who wanted to use that data between 1994 and 1998 were a little more annoyed. And it was being over budget was a little more severe. Instead of $12 million, the project as a whole took more like $80 million. Jim Gunn will maintain to this day that if they knew that it was going to cost $80 million, they never would have done it. And so it was good that they misestimated the budget. which I kind of disagree with, but you know, they did get the money to do it from the Department of Energy and from the Sloan Foundation and from NSF. And Sloan and NSF had conditions, and the conditions were, you know, this was a project with like 4 universities. The conditions were you have to release the data. You have to make the data available to all the astronomers and everybody. And so they needed the money, so they agreed to that. Oh, and over the course of the project, those 4 universities had to also grow and in order to fully fund the project, because they needed new university partners who would put in yet more money to make the whole thing happen. Those things turned out to be really good changes to the project. Releasing the data was probably the best thing that they possibly could have done for their long-term health, and growing the partnership as well. It's a very resilient partnership now. We have, as I'll show, you know, where they are on the Earth later, but you know, it's a partnership of 70 institutions now. So the first phase of the project, though, was concentrated on imaging and spectroscopy. And so here's sort of the summary image, which we made, you know, shortly after we finished the imaging survey. And this is, you know, the actual images are showed on the top here. You know, there's a zoom in to NGC 604, which is this star forming region in Messier 33 in Triangulum. And so that sort of shows the multi-band imaging that you get on, you know, it successively zooms out. And this is just a small part of the you know, mouse of some sort. Oops. A small part of the full imaging survey. And the footprint is shown here. This is the southern galactic cap, the northern galactic cap. So these are both from a northern perspective, so they overlap a little. But these caps are distinct. And what's shown here is not the image, obviously. Here, these are just number counts of the galaxies shown projected onto the sky. So you take the images, you find the galaxies, you count them up in little cells, and this is a map of the large scale structure, which is what they were most interested in at the beginning of the project. And you know, you see, you know, clusters and voids and filaments and all the beautiful structure that, you know, cosmologists really like to measure extremely carefully. So this is sort of the SDSS version of the Shane-Virtanen maps, if you've ever seen those old maps from the 70s. For about 1 million of those galaxies, the brighter ones, we got spectra and therefore redshifts. And so this is sort of the closer, you know, a slice along the equator of the closer set of these galaxies. And again, in 3 dimensions, you really see the detail and the voids. This image, the colors are the intrinsic color of the galaxy. And so you see the red galaxies concentrated in the clusters, the old systems, and the blue galaxies filling out the filaments more prominently. You also see there's a trend here, because the closer galaxies, close by, we can see the lower luminosity galaxies, which tend to be bluer galaxies, the smaller galaxies. And the further away ones are big, bright red galaxies. So this structure is really what the initial project was interested in measuring. Now, throughout the, you know, from the beginning, you know, at the beginning, we were looking at very nearby things, but we learned over time that we could look further and further away and select galaxies to be further away. And we could get spectra, not as good spectra, but spectra good. And we realized that we were taking spectra that were much too good. And so we really could go much fainter and further away. And we also realized we could use not just galaxies, but quasars, which are intrinsically much more luminous objects, to actually map the universe on the largest scales. So up to about 2019, we were doing things like this. And so we could sort of make bigger maps. So the center of this map is us. Around that is basically the image I just showed. And then as you zoom out, you see more and more structure, or more and more volume. The red points are the galaxies. The black points are the quasars. And we can do large scale structure. I mean, it looks very uniform because it's a very large volume, but you can do large scale structure, out here. You can detect the clustering of these quasars. You can look at what's called the Lyman alpha forest to see the structure of the gas in between the quasars. So this is cosmologically extremely powerful. In fact, this image is a slice through the entire observable universe. This thin circle on the edge is the limit to which photons could actually reach us. They don't actually reach us because there's, the gas is ionized. So what's shown here is the temperature of the cosmic microwave background at that distance. And this is what we've actually ended up mapping in SDSS. It's a slice, so it's two-dimensional, so it looks like it's quite a big fraction of the volume. In fact, it's a few percent of the volume of the observable universe. A few percent isn't that much, but I mean, it's the whole observable universe, so, it seems respectable. Nowadays, this sort of work, after 2019, has been taken over by the DESI project, which is on the MIAL 4-meter telescope at Kitt Peak. So they do something very, very similar, but with a bigger telescope and many more fibers. And I'll explain what we are doing now. This sort of work has gone to bigger telescopes, and they're gonna take what we did and do like 50 times the size. So the way we did this, is we use these spectroscopic plug plates. So you have a big aluminum plate. It's got a bunch of holes in it. The thing's going to get set into the focal plane. In each hole, there's an optical fiber plugged. So first you take the plate, you have to draw on it to make sure you can plug the plate properly in the right order. Then you plug it by hand. This took, when they were doing this took about 45 minutes a plate. It was full-time jobs for a couple people on site. They would come in and plug plates all day. Then they get put in these cartridges, the plates sitting here, the fibers come down here, and they come out arranged here onto a slit head, and those are what feeds the spectrograph where the spectra are actually taken. So the light is going to come down when it's in the telescope, it comes down here, and then the fibers bring it out in a nice orderly fashion along the edge. These would live in a little bay, and during the night, someone would have to take them out. They're a couple 100 pounds each, so you use some robotic arms to do this for you, bring it to the telescope, and trade out the cartridges. Whole thing took about 20 minutes to do that, and you do that maybe, on the best nights, you do that 10 or 11 times a night. Just so you can, we had a video of time lapse, obviously, of someone plugging one of these plates. And, we got clever over time about the colors, different objects, and this is a whole complicated mess that I spent a really disturbing amount of my time worrying about. But after you're done, you could, we had all these, every time we observed a different patch of sky, you need a different plate, right? So we ended up drilling we had these high precision drillers. You had to put the holes about 10 micron precision on the plate. And we made about 13,000 of those things over the course of, that 20 years or so. in each hole, you get a spectrum. This is just an optical spectrum. This is a galaxy. It looks like it's at about redshift 0.5 or something. This is what we're using to map the universe. You know, these features, these are the H and K calcium lines. Those are around 4,000 angstroms rest frame. So using Doppler shift, you figure out that this is about a redshift of 0.5. And that's how those maps are made. But of course, for each plate, you have 1,000 holes. And so you get 1,000 of these spectra. And so it's where did that low image come from? Okay. You get 1,000 of these spectra. And so there's a lot of information on each plate. This is just one that was observed in 2012, I guess. So when you're done, you got a bunch of plates. We scrapped a lot of them, like literally sold them to companies to scrap for $5 a plate, which didn't seem like the best idea. But other ones people took home, made art out of. This is, I believe it may still be, but for a while it was in LACMA, which is the LA County Museum of Art. I think it may have been in the Met for a little bit. This is a sculpture did this. This is the spouse of one of our engineers, who's also a sculptor in Seattle. She made a replica of the telescope aperture with plates. This engineer had like all his office stuff, the thing that held his laptop and all that was all made out of old plate material that she had made. Anyway, I feel like the best use are these little coffee tables. It's sort of perfect coffee table size. But we also sent them to a bunch, probably at this point, about 400 astronomy classrooms throughout the world for reasons, a lot of them in northern Scotland. Just because we have a very, very good team at St. Andrews who's really interested in doing this. And so they get it with some material, some like curriculum material, and they have a plate, and they can use our databases online to like look up the objects on their plate, learn about redshift, learn about galaxies, learn about colors. So the plates are like nice little artifacts. So as I said, at the beginning, the project was demanded that they actually release all their data publicly. We're now on data release 19. There are databases online. There are interfaces for looking at the spectra, and for certain classes of galaxies, like actual maps of spectroscopic maps of the galaxy. As I mentioned, the Plates for Education program. There have been about 13,000 papers from the data sets we've released, and 10% of them are from our collaboration. The 50, 70 institutions are involved, but actually 90% of them are other people using the public data. And that's what's been keeping the foundations and coming back to fund us, because this is a 10 times increase in the scientific impact of what you're doing. Because we have a lot of people in our collaboration, but there's a lot of science to do with this amount of data. So it's a very scientifically effective thing just to give away your data and document it really, really well. So every year we get together and we have a festival, a documentation festival. We get snacks. We get snacks from Scotland and from Holland and from wherever the leads of this group happen to be from at this time, and just lock ourselves in a room to just write documentation about the data. And so it's a very committed group of people who do this. I think we pay this person, that person, a little bit of the other people, but a lot of the work that goes into this is more or less volunteer. People are interested in the science, interested in making the science available. They have jobs as professional astronomers, but this part of their work is volunteer. And as I said, this is I basically already said this. This is, there's 70 institutions across the world, most of the continents. We had a star down here in South Africa for a while, so we kind of had all of them, but it's very widespread. And you'll notice there are a whole bunch down here, which is obviously Chile. And those institutions came in when we expanded in the mid-2010s to the Southern Hemisphere. And as I said, here's sort of a, the northern sky, the southern sky. This is, the rendering of the galaxy. And there's a lot more galaxy down here. Here's the galactic center. Most of the stars are really, most easily visible from the southern hemisphere. And as it was clear that bigger projects were coming to make large-scale maps of the universe, we realized we were going to have to be doing something different that was also interesting, which was mapping the galaxy. And to map the galaxy most effectively, you want the north, because there's galaxy in the north, but you really need something in the southern hemisphere. And so this we ended up doing at the Las Campanas Observatory, which you can see here. And these are 6.5 meter telescopes. Those are the Magellan telescopes. We're not using those. We're using this one way down here, which is a 2.5 meter telescope, like the Sloan Foundation telescope. Inside the dome, it looks like this. This was actually a telescope built in the 70s, which was actually the starting point for the design of the Sloan telescope, and had done a prototype survey that did CCD imaging and fiber spectroscopy around 1990, before SDSS started. So almost everything about this was the prototype for SDSS. They did a small project with what they had done. Then they went on to do other things. And then we came back in starting in 2016 or so, and basically, brought that technology back to DuPont and in order to do this project in the southern skies. So we ended up building, we had at that time an infrared spectrograph in the north. We built a twin of it and put it in the basement of this building. It's a big thing, big cryogenic thing. And then put all the plate system stuff and put this plate system so that it was at the focal plane of this telescope. We had to operate there, and it turned out we didn't actually have a business presence in Chile, so we had to figure out how to employ people there. We worked with a bunch of, in the end, about 9 Chilean universities. During this time period, Chile had really decided to build up its astronomy. It had had a couple of astronomy departments for a very long time. And the Europeans and the Americans would come in and build their telescopes. And the Chileans would get like 10%, but they didn't have a really active astronomy science community. And then, starting about 15 years ago, the Chilean government said, you know what, they weren't intrinsically interested in astronomy, but they wanted to have more Chilean talent in science and engineering, because in addition to astronomy, they had all these mining companies, and they wanted more Chilean presence there because they didn't want to be quite as dependent on other countries and the multinational companies. And so part of their strategy was fund astronomy, have lots of astronomy departments, bring students into science that way, concentrate on astroengineering, so like building stuff for telescopes, and bring people into science and engineering that way, who then would go and, some of them would succeed in astronomy, but a lot of them hopefully would go off into industry. And so that led them to fund all these astronomy departments. And I have to say, having worked with a bunch of young Chilean engineers, it's really true. Like there were a number of students who came in and this is how they got their feet wet doing astronomy stuff. And now they're working for some company. And it worked really well for us because these universities were really interested in being part of our project. And so they were providing observers and engineers to help us. Now we have a more full partnership. Basically, every astronomer in Chile is a member of SDSS. And what this allows you to do is look at the entire galaxy. So instead of just the northern part, which would be visible roughly where I'm showing here, you can really get at the galactic center from the southern hemisphere. The things we actually do are we take these infrared spectra. So this is a spectrum around 1.6 microns, 16,000 angstroms. And these are a bunch of stars of varying metallicities, things that are very, very metal poor at the top, so pristine-like things, to things that are, roughly the metallicity of our sun. And you can determine the metallicity, the velocity of the star, even the age of the star, it turns out, like an individual star, from these spectra. And then you can make maps of the galaxy. So here's sort of a projection map. We are here, the center of the galaxy is here, and this is colored by age. So you see the disk of our galaxy, and the thin part of the disk of the galaxy is very young, and you can see the age gradient as you go. And you can even see this thin disk of part of the galaxy start to flare out at high radii. So here you can see the structure of the galaxy, but you're also seeing sort of its structure over time. And if I can get even more technical, we can get the metallicities, like how many high mass elements there are, like oxygen, and you can get the age. Now, as stars form, like the gas from which stars are forming enriches because of previous generations of stars. So if you have a lot of oxygen, it means that there was some previous generation of stars that provided the oxygen. And so what you expect over time, the stars go around the galaxy in roughly circles, and so does the gas. And so you expect over time that the first stars to form, what are now the oldest stars, should not have very many metals, right? Should be not very enriched. And over time, they should become more and more enriched. So you should see something a little bit like what you see here in this bin here, where the oldest stars, this is age, the oldest stars are metal poor and the youngest stars are metal rich. This panel, which is repeated here over and over in different parts of the galaxy, because we have this whole galaxy to do this in. And so this is radius from the galactic center. This is distance from the disk plane. We live in this box, about 8 kiloparsecs, or 8.5, and near the disk plane. And what you see here is that as you go in age, as you get younger, you get more metal rich, until here, where the most metal rich stars are actually a little older than these stars here. The sun is 0 in these units. And so what you're seeing is this model where things just enrich over time is broken. It's a long story behind that, but we think the reason it's broken is because these stars have wandered from the interior of the galaxy. They look like they're going around in circles. They don't look like they're going back and forth in the galaxy, but something has caused them to change from going around in circles in the center to going around in the circles further out. This is called radial migration. And there are mechanisms to cause it. Spiral arms can cause stars to change their orbits in this way. But this is a detection that it's actually happening. And you see patterns like this sort of all over the galaxy. And so what the science teams try to do is they try to take models of the galaxy and see if they can explain these patterns. But it involves these complicated dynamics to untangle the history of the galaxy. How much time do I have? Yeah. Okay. um, so, well, I'm up to 2022, so it can't be very far from the end. Okay, so we did this survey of galaxies. We started doing this survey of the Milky Way. We went to the southern hemisphere to do a better survey of the Milky Way. And then we kind of realized we wanted to do that survey faster. We wanted to cover the whole sky faster because these plates, you know, it takes 20, 25 minutes to change a plate out. And then it, you know, if you want to do a short exposure, if you want to do only 15 minutes, it feels kind of wasteful to look at the sky for 15 minutes, change out the plate for 20 minutes, look at another part of the sky for 15 minutes. Seems like you're wasting a lot of your night changing out plates. So we wanted a way to take shorter exposures. Our old exposures used to be about an hour because that sort of made sense. Then it was like a small amount of time you spent taking, changing out your plates. We wanted to take these shorter exposures, then we could do more sky. We could do the whole sky faster instead of just like little pinholes through the sky, or what is the word? Pencil beams through the sky. So, and another technological development was happening is that people could make precise small motors much more cheaply by this point. In fact, the DESI project was basing their whole project on these robotic fiber positioners, not these ones, but something similar. And so what we decided to do is we decided to change over to these robotic fiber positioners. So they each cover, the way they're designed, they each cover a little annulus on the sky. And then you put them all together to cover, your entire focal plane. So all these annuli. And in fact, each one has two fibers, one for the optical spectrograph, one for the infrared spectrograph, and you could pick which one you wanted to use. You can pick whichever one you want to use. So these got built. They got built sort of mostly during the pandemic, which was an interesting process. This is the one that got sent to, this is happening at the Ohio State University. And that's where these were built. And this one got sent to New Mexico. This is the team that, some of these are engineers on the team, but all of these people helped like install. I should have gotten a picture of the backside because it looks so orderly here. You see the fiber, the fiber positioners in this nice little hexagon pattern. The backside is just like 1,000 little thin fibers like coming out in this, what looks like a gigantic mess. So you have to be very, very careful when you do that. Here's the one that went to the southern hemisphere. And then here is a picture of it in motion. They're all at home. And then you tell it, oh, I want to place each fiber where I think a given object is going to be. And you can see the fibers, the tips of the fibers moving around, to get to where the objects are anticipated to be. And you have to do this with all the robots not hitting each other, which was Connor Sayre's PhD thesis at University of Washington, was figure out how to make the robots not hit each other, which he successfully did. They basically never hit each other, which is amazing. And this takes our overheads, these 20 minutes, down to about 5 minutes. about 30 seconds of it is doing this move, and the rest is calibrations we have to do anyway. And moving the telescope, slewing the telescope takes some time. Let me do this. What is this video? Ah, yes. And then we can cover the sky. So this starts in early 2022. We started in the north, installed it there first, and you can see it's like a little bit slow at first because we couldn't place the fibers exactly where we wanted, so our signal and noise wasn't so good. Then later in 2022, we've installed in the southern hemisphere down here, so we actually start observing there. At some point, and then we're tootling along, and then at some point, basically a year ago, we start going fast. That's about, in this video, it's not going to be dramatic. I don't know why I'm doing this, but it's about now. We started going a lot faster because we figured out how to place things correctly. Also, we put these green stars on the plot. These green stars are where there's been a transient object, some object that's doing something exciting, like a supernova has gone off or something like that. And then basically once or twice a night, we take a fiber we were going to observe some star with, and then we say, no, let's look at this, target of opportunity. So that's something that I think will be really important for the future as these time domain imaging surveys become more and more common. But in terms of the galaxy, the aim is to take a map that kind of looks like this. If we look at the galactic plane, this is what we did in SDSS 4. SDSS 5 is going to fill this out by being able to cover the whole sky, so you get a more continuous map. And it's also going to be able to look deeper into the galaxy. So that's the aim there. I'm going to skip that. But then somebody had a whole different idea, because the galaxy is made of stars, but there's the gas that the stars are forming out of. And that gas is interesting too. Like, you can determine the metallicity in that gas. You can determine how that gas is lit up by the young stars around it. And you can understand the history of the galaxy by looking at the gas that's forming stars right now. And there are ways of looking at this with radio observations and infrared observations. We are looking at it through the optical observations, which is really showing us about the ionized gas in the galaxy, of which there's quite a bit. And this is basically what this does is it takes a spectrum of every point on the sky in the field that it observes and makes a continuous map of spectra across the sky. And by analyzing the spectra, you can determine the properties of the ionized gas along the line of sight. And so this is what the focal plane looks like. And it's tiled with a bunch of fibers, 1,801 fibers. You just figure out the kinds of numbers you can make hexagons out of. 1,801 is one of them. And it covers half a field of view. I didn't include this, but this, of course, this is astronomy units. So I don't know about you guys, but professional astronomers, when we talk about big areas on the sky, we talk about full moons. So this is like one full moon. And I used to joke well, but we're not going to point it at the full moon, except last year during a lunar eclipse, we did actually point it at the full moon, because then you get a spectrum of the sun through the Earth's atmosphere reflected off the moon, which turns out to be interesting to climate scientists. So who have been monitoring just that spectrum for a long time, but on particular spots on the moon. And so this allows you to sort of relate the albedo across the moon spectroscopically across its, as a function of where you're looking. so this ends up using several telescopes. Sorry, the telescopes are over here. The nomenclature is a little weird for me. These are not really telescopes. They're just siderostats. So these are just things that it's an alt configuration. And then you can think of the telescope sort of being in here. And then there's a focal plane that sits here, and fibers come out. And a bunch of fibers come out of each of these, and they all go here, and they get redistributed to the spectrographs, which actually take the spectra. So this is a very unusual looking telescope because it's got these 4 siderostats. The telescope part of the telescope is really in here, the focusing part, and these fibers come out to the instrument. But it's very, very stable because these siderostats have to move, like this pair of mirrors, but nothing else has to move. And that's really great. You don't have to worry about cables wrapping around, all that stuff. So here's the DuPont telescope where I was talking about before. And then there's a ridge here called Robot Ridge. There's all sorts of robotic telescopes. And this is the local volume mapper here. This is where the Polish astronomers live when they're on site, which there's always at least one Polish astronomer, or an astronomer from Poland anyway, at Las Campanas. Here's a close-up of the instrument. So you see this is the as-built, so the siderostats. Here's the telescopes, and then the spectrographs are back here, closed up, obviously. When you're done and you take an observation, this is Rosette. This is the Rosette Nebula. This is how it is in H alpha. And so you see all this beautiful structure. This is O3. So this is, a nice, this green line. These are the strong lines. They tell you, a lot about the ionizing flux that's coming out, that's ionizing this nebula. You can look at fainter lines. They end up being a little blurry because you kind of have to average over more of the spectrum. Each of these hexagons that this is tiled in is one of the observations. And then you do a bunch of observations and tile them together. These are what's called the auroral lines. So these can tell you things about the temperature of the gas. And these are the faintest lines. These are called recombination lines. They are basically telling you very, very directly how much ionized carbon, singly ionized carbon there is, how much singly ionized nitrogen there is. They're almost a direct measurement of that. And they're the gold standard for measuring the metallicity of a system of gas. So we can detect this and learn a lot about what's going on in these systems. And this is going to observe a big swath of the Milky Way, this footprint here. It's basically done all of the Orion Nebula and surroundings. It's doing the large and small Magellanic Clouds. I forget what we observed here. And within the Milky Way, it's getting to, less than a parsec physical resolution. So it's really doing a detailed map of the Milky Way. What? Oh, I don't know. I should know. Okay. Yeah, you should never walk into a room of amateur astronomers and not know what every object on your screen is. It's a big mistake. Yeah, so as I said, every 5 years, we've got to reinvent what we do, and we get new leaders, a new set of projects. We usually build something new. We try to get new funding. And we've, and the Sloan Foundation, I don't know if you've ever seen The Princess Bride, But the Sloan Foundation's attitude towards us is basically, good job, sounds great, probably won't fund you next time. But they kept funding us, so I think we have some exciting plans for the next phase. You know, we'll end SDSS 5 in 27, and we're going to try to do the far side of the galaxy. If you look back at this map, you know, we want to do these parts of the galaxy. So go deeper just in the disk plane, because, you know, you don't get something for nothing. But if we concentrate there, we can go pretty deep across the other side of the galaxy, which no one's ever done before. We want to detect, you know, go after transients. The Rubin Observatory is going to have a ton of transients. Many of them will be super faint. We won't be able to see those, but a lot of them will be very bright, and we can follow those ones up. We want to design a version of the local volume mapper, which does the same thing, but on a bigger telescope. These little telescopes have a wide field of view. You can take the same F ratio with a big telescope, get a small field of view, high resolution, and you can do Andromeda with the local volume mapper. And we obviously do that on some northern telescope, TBD. And there's a project, which I won't explain, to do the nucleosynthetic history of the galaxy. So we're really excited about doing all this. We're hoping that we'll be successful in getting it all started. So wish us luck. Thanks.
Any questions in the room? What about these discs?
They're like this big. They're made out of aluminum.
The question was about
Oh,
the swapping
sorry.
out of the discs. We just want to repeat it.
Oh, sorry. Yeah, the question is about the swapping out of the discs. So the way it was set up, so we don't do this anymore. We're just using the robots. But the way it was set up is we would have, you know, we had 17 different cartridges. And what you would do is you take the disc, which is about 80 centimeters in diameter, and you'd install it in the cartridge. It had to be put under some amount of pressure to get it to the right shape. And then you would plug it, and you do all this during the day, and the fibers would stay in the cartridge. And you would then have prepared that plate in that cartridge for some particular field. And you'd have probably 10 or 11 of these ready on any given night. So you'd spend the day doing the plugging. And so we had, you know, if we had 1,000 fibers for a plate, we had, you know, a set of 1,000 for each cartridge. So you didn't have to replug it during the night. You just took this whole system, the whole cartridge, and, like, you know, replaced it. And the plugging had already happened. It was a very clever way to do it, because, yeah, doing the replugging during the night would be painful. Well, the fibers come in these little aluminum, sort of 2 millimeter size aluminum pieces of metal, which are called ferrules. And so the fibers installed in that, they never leave that. They're like glued in it. And those things, so they're there to protect the fiber so you don't break it. And then there's a very slightly larger hole in the aluminum plate, like larger by tens of microns. And then you plug it into that. It has to be, you know, and we spent a lot of time figuring out exactly the right size and what type of aluminum, and because it has to kind of stick in there, you know, easily enough that someone can plug a bunch of them, but it also can't fall out. So it's like very finely tuned. It's an interesting analog type of problem to, you know, to get that just right. They're even, the way they are installed in the cartridge is even designed so that they're biased a certain way, so that the tilt of them keeps them, you know, keeps them from falling out. like actually that slight amount of tension on the fiber. Oh, they're behind you. Yeah. Yeah. So interestingly, the difference here is between these two is not so much how faint the objects we're looking at are, it's just simply the number. There are just so many more on the right-hand side that they end up reaching further. Now, as you say, in the disk plane, it's very crowded. Certainly, well, two things. One is there's dust, right? You go out and you look at the Milky Way, you see like the dust bands. You can see those visually with your eyes. So those will extinct the light. That is the reason we're working in the infrared, because the dust is very fine, like it's extremely fine. It's like a tenth of a micron or less, most of the dust. And so 1-2 micron light goes around it a lot more efficiently than visible light. So that extinction is a lot less. And also the crowding ends up being a lot less as well. But crowding is definitely a problem. It's very often you're taking a spectrum and you're kind of getting a spectrum of a number of different stars. And that can be hard to account for occasionally. But so far it hasn't been too bad. So an arc second, these things are 2 arc second fibers. So, it's the crowding is, not so bad at that level.
Could you describe describe the computing pathway, because the first correspondent told me that the analysis of the galaxies is done by computer.
Oh, yes. Yeah, so the question is about the data flow and the processing of the data. So the data is stored on the mountain. The data is taken on the mountain. It is, delivered through, I think basically rsync, just delivered over the internet to a set of computers we have at the University of Utah. They are then backed up at the, the national lab at Lawrence Berkeley Labs onto tape. They still have like these giant tape archives, like tape, those reel-to-reel things. Like they still have those. They're still extremely useful. So we do all our like deep backup there. We make a copy at Johns Hopkins. And then the data gets processed mainly at Utah. So every night you process the data, somebody looks at it, make sure it looks okay. And that's where, you extract you make the individual spectra, and then you process the individual spectra to figure out the velocity, the metallicity, the blah, blah, blah. And then you make big catalogs. Those big catalogs and all the underlying data eventually get made public. They're put in a database that's available on something called Sky Server and now Sky Server, which are both done at Johns Hopkins University. And that's where your typical person will get access to the catalog. Does that answer your question?
Program to analyze it a certain way.
Yes, it's
every once in a while there's an error like being counted.
Oh yeah, so it's been programmed to do specific things, some of which is just to create the spectrum. And then from the spectrum, you want to know, say, the redshift. Obviously, sometimes the redshift is wrong because it's computer. Actually, sometimes people get redshifts wrong too. But there's a, you have to infer the redshift. And in that particular case, if the spectrum has some artifact or noise that it doesn't know is there. Or it's just an unusual spectrum, like some, binary objects can look unusual. And sometimes the pipelines just barf. They're just like, and sometimes they're like, I don't know what this is. And sometimes they're very confident of what it is and they're wrong. So. We're not using those so much in the creation of the data set because we usually want that to be pretty deterministic. But in terms of classification, things like that problem, is this correct or is it not? Like, is this, those sorts of things on the post-processing side, they're very commonly used now and very effective at saying, oh, this is just a common error that we've identified. And because, early on, I looked at probably, I don't know, like tens of thousands of galaxy images, like picking out ones that the imaging processor had done wrong. And nowadays, I would do 1,000 and then train some AI to do it the way I'm doing it. Yeah. No, we look for this phase of the project, we're looking pretty much pretty much everywhere. So as this fills in, you'll see we have you'll see the galactic plane appear, but you see we're looking elsewhere as well because we're also interested in the stellar halo of the galaxy. So we're actually looking all across the galaxy. But we do spend an inordinate amount of time in the galactic plane because that's where most of the stars are. So you kind of, some of these fields we go back to 90 times, just, to get the number of stars that are there. Other galaxies for this particular phase, there is part of this phase where we're looking at quasars, and we end up taking spectra of galaxies. I think for mapping the universe with galaxies, it's really the bigger telescopes that got to do that now because they're just they're faint, and we've gotten most of the bright ones already. And so if you want to go faint and far away, you really just need a bigger aperture, and there are a lot of them, so you need bigger fibers. So. Yes. So to measure that, there are ways that from the spectra you can estimate, you know how bright the star is from its image, and from its spectrum, you can determine, where it is in the Hertzsprung-Russell diagram. So you can determine what its luminosity should be. And so you can actually use the flux and the luminosity to get a distance. Those are fine at best, maybe 5 or 10%. Most stars, it's probably a little worse. But for many of these stars, the distance we actually get from Gaia, which is the astrometric satellite. So many of these will have a parallax from Gaia, and those, I mean, it varies. Like for many of the things in the plane, Gaia is visible and we're infrared. So we have many things in the plane that they don't have. But when they do have a parallax, we definitely use it.